We're going to look at chapter 11 today. So, chapter 11 still kind of carries on the alkyl halides chapter. So, alkyl halides are electrophilic. So, we've solved that before. So, if you have an alkyl halide, okay, so alkyl halide, you have a halogen attached to a carbon, have a polar covalent bond, so bromine's more electronegative, so it pulls electrons towards it. So that means it has a partial negative charge, giving that carbon a partial positive charge. And so that's what's meant by alkyl halides are electrophilic. When true with a nucleophile or base, they'll either undergo substitution of the X group on the nucleophile, or they undergo elimination of HX to yield an alkene. And so we'll have two different types of reactions, substitution or elimination. We'll look at what conditions favor each of those mechanisms. So these two reactions are rapidly occurring and very important to the study of organic chemistry. And so whereas, like the previous chapter, like when we looked at alkenes and we looked at a lot of the reactions, you could make flashcards and just basically memorize those reactions and do fairly well on the exam. On this one, you really have to kind of understand the mechanism. And so what you have to make flashcards for is not reactions, it'll be what conditions favor certain mechanisms. So at the very end, I'll make a table over the different mechanisms, and that's the table that you'll need to know for these reactions. But the first thing you'll need to know is be able to recognize the electrophile and be able to recognize a nucleophile. So remember, nucleophiles, extra electrons, something with a minus charge. Could be a pi electrons of a double or triple bond, or it could be just a lone pair of electrons like oxygen or nitrogen or sulfur. Electrophiles will be something like this, have halogen attached to it. We'll look at some different examples of it. We're going to call this a leaving group, because when it substitutes on, the halogen will leave and take the charge by itself. So we'll call the halogen a leaving group. So when we look at substitution reactions, we got two different types of mechanisms that the substitution reactions can take place by. And they're called SN1 or SN2. SN2 is short for, the S stands for substitution, N stands for nucleophilic, the 2 is bimolecular. Okay, so just SN is talking about nucleophilic substitution. Your nucleophile is substituting one in place of your leaving group, which is commonly a halogen or it could be a tosylate. And so this would be a good leaving group too, this OTOS. And OTOS is just abbreviation for this large substrate here. Okay, so there's oxygen. This is the tosylate part. But instead of drawing all this out, you'll just see OTOS really. So in the mechanism, so I'm going to have some kind of a carbon that has my leaving group attached. Leaving group is commonly a halogen. I have some different things attached here. I'm just going to make them R groups. Then I have to have some kind of a nucleophile. So in the SN2 reaction, the substitution takes place in a single step without intermediates. So it substitutes on in place of your leaving group. Since your leaving group is on one side, the nucleophile attaches, when it attaches all in one step, must attach from the opposite side. And so we say that this reaction occurs with the inversion of stereochemistry. Okay, so it attaches from this opposite side. And so if this was a chiral carbon, if all these R groups were different, this was a chiral carbon, that would mean if you had an R here, assuming all your priorities stay the same, then over here you'd have the S. If you start with an S here, after reaction you have the R. Again, assuming your priorities stay the same. So you have this inversion of configuration. The transition state for that, you just draw your nucleophile starting to form bond to a carbon and the leaving group bond starting to break. Commonly when you show the mechanism, you don't show the transition state, so there's no intermediates there. The reaction shows second order kinetics is dependent upon both the concentration of the substrate and nucleophile. I put Rx, I probably should put CLC or LG there, but this is your substrate. Okay. This is your nucleophile. So this is just your concentration by some rate constant. So if you double the concentration of your substrate, you double the reaction rate. If you double the concentration of your nucleophile, you double the reaction rate. If you double the concentration of both of them, you quadruple the reaction rate. So it's dependent upon both. And so that's where the bimolecular comes in. Okay. So one thing that can be confusing is that the SN2 mechanism takes place in a single step, one step, whereas when we talk about the SN1 reaction, it takes place in 2 steps. But that's because the bimolecular is dependent upon 2 different molecules, the reaction rate, whereas the SN1 will only be dependent on 1 when we get to it. So that's why the unimolecular comes from there. Now this mechanism takes place from attachment from the opposite side. So if all these R groups were hydrogens, it's going to take place faster. The bulkier these R groups are, the less reactive it's going to be because it has to attach from the opposite side. So you have a lot of carbons here. It's not going to take place very quickly by this mechanism because it's too sterically hindered. So methyl is going to react faster than primary, okay, which will faster than secondary. And so you actually don't see really tertiaries react by this mechanism because they're too sterically hindered. Let's go ahead and look at a problem from your textbook. So this is 11-1. What product would you expect from nucleophilic substitution reaction of S2-bromohexane with the acetate ion? Assume that both inversion of configuration occurs and show the stereochemistry of both the reactant and product. So the first thing I have to do is draw out S2-bromohexane. So I'm just going to draw one of them. So I'll put my bromine on the wedge. That way I can do R and S configuration. So bromine's my top priority. And 2, 3. So that's clockwise. So that's the R configuration there. So I know to get the S, I can just invert that stereochemistry. So there's S2-bromohexane. Now it says I react that with the acetate ion. So the acetate ion, I have a minus charge on the oxygen. So where that minus charge is, that's going to what is attached in place of my bromine. And it attaches from the opposite side. So that means if my bromine's on a dash here, my acetate ion will be on a wedge. So now if I did the RNS configuration of that one, I'd see that I get the R product. So I start with an S again R, that's because it takes place via an SN2 mechanism. So these reactions, you just have to be able to recognize, okay, I have an alkyl halide, I have some kind of a nucleophile, I have something with a minus charge here. So what has a minus charge substitutes on in place of the bromine. Or if you had something with a long pair of electrons, like H2O, that's what would substitute on in place. So you just have to be able to recognize nucleophile, and then we'll determine if it's going to be substitution or elimination. Look at another one. Let's look at 11-2. So what product would you expect to obtain from SN2 reaction hydroxide ions or 2-bromobutane? Here's 1, 2, 3, and so that one is R. Hydroxide. So what's going to substitute on in place of my bromine? OH. OH. It's going to be on a wedge or a dash? Dash, okay, because it must attach from the opposite side. Go ahead and look at some more characteristics of the SN2 reaction. Because it attaches from the opposite side, SN2 reactions take place only at relatively unhindered sites. So if it's tertiary, it's not going to work as well. Finally, aryl halides are unreacted towards SN2 reactions. So this is very important here. If you have your halogen is attached to a double bond, it does not undergo substitution reactions. So, halogen attached to double bond, no substitution. Nucleophilicity roughly parallels basicity, meaning the stronger the base, stronger the nucleophile. Nucleophilicity usually increases going down in the column in the periodic table. So if you're comparing like OH minus to SH minus, S is below oxygen in the periodic table, so it's a bare nucleophile. Negatively charged particles are usually more reactive than neutral ones. So that's talking like if you're comparing OH minus to H2O. Both substitute on an OH group, but the OH minus is going to be a much more reactive than the water itself. So when it talks about neutral, it's talking about something without a charge. Neutral means no charge. So negatively charged particles more reactive than those with no charge. Leaving group reactivity tends to increase with size. So we're talking about halogens here. So if I look at fluorine, that's one of my halogens. I call the reactivity of fluorine as a leaving group 1. If I look at chlorine, okay, we're getting larger here as we go down the column of the periodic table. Chlorine is 200 times more reactive as a leaving group. Bromine 10,000 times more reactive than fluorine. Iodine, 30,000 times more reactive. And that tosylate that I showed earlier, 60,000 times more reactive. So it's a very good leaving group. Things
That's
like
a product solution or solvent, right?
do what?